we are going to start with the basis of linear algebra classes, which is nothing but vector spaces. So, as a startup, we are going to define what vector spaces are and just discuss some among the examples which are often famous while dealing with vector spaces, and then see how we can work out more in the exercise session of the same area. So, vector spaces is actually closely associated with linear combinations of rows of a matrix. Matrix you all are familiar with, and you now have got a good knowledge that what you're going to deal with the subject is closely associated with matrices, and uh, obviously they'll be related to matrices in some way. So as we see, linear algebra is a branch which deals with algebraic systems, which consist of a set and some linear combinations of elements in that set. So, how will we rigorously define a vector space? So, to define a vector space, we need three things, three basic things. What are the three basic things? The first is a set of scalars. First is a set of scalars, and we know that it is a field f of scalars. Field is an algebraic structure we have dealt with while we were doing our algebra classes during the degree program. So you know what a field is first of all. So you need a field, and the elements in the field we call here as scalars, the elements of the field. Okay, the next one is a set V of objects. Okay, let we call it as a set. Okay, a set of objects. So the set of objects here we call it by the name vectors. Okay, so set of objects. So you have a bunch of scalars, then you have a bunch of vectors. And the third thing is the rule of, I'll call it the rule of connection between 1 and 2. Okay, so you have a field of scalars, constants, then you have a set of objects called vectors, and the third is a rule which connects these scalars and vectors together so that you can form a structure which has some connection to each other inside. Okay, so what is the rule? Okay, we are going to talk about the rule now. The rule we talk about first is the vector addition. That means which associates with each pair of vectors alpha beta in V, alpha plus beta in V, and it is called the sum of alpha and beta in such a way that alpha plus beta is equal to beta plus alpha, then alpha plus beta plus gamma is equal to alpha plus beta plus gamma, and there is a unique vector 0 in the set of vectors such that 0 plus v is equal to v plus 0 is equal to v, or call it alpha. Alpha plus 0 is equal to 0 plus alpha is equal to alpha for every alpha in the set of vectors, and for each vector alpha there will be a unique vector called minus alpha, where alpha and minus alpha are summed up, you get 0. Okay, so the rule of connection. So you got the first rule which connects all the vectors in between, and that's called addition. That's what we said now. Now there is a second rule which is the rule of scalar multiplication, and that happens in between the scalars and the vectors. So how does that apply? With each scalar C in F and each vector alpha in V, C alpha will be in V, right? So C belongs to the set of scalars, and alpha is a vector in the set of all vectors. If this is happening, we know that C alpha will be inside V, and we call it the product of C and alpha, and it has this operation as some four properties, which are 1 into alpha is equal to alpha for every alpha in V, where 1 is the multiplicative identity inside the field. Being a field, it will obviously have a multiplicative identity. Then the B says if C1 C2 into alpha is equal to C1 into C2 alpha, C into alpha plus beta is equal to C alpha plus C beta. Then C1 plus C2 into alpha is equal to C1 alpha plus C2 alpha. So from this, you have an inference that what are the inferences? You have the set V along with the vector addition, which is the operation we talked about at first. So V along with the operation vector addition is an abelian group. So this is an inference, right? And then we have obviously another thing associated with this, that is F, right? So we know that F is a field, and obviously F star with the multiplication there is an abelian group. Obviously it is cyclic, right? F is a field. F has addition and multiplication together being a field, and from that earlier we had done in the algebra classes that F star and dot will be a cyclic group. Similarly, that's what we said. If it is cyclic, then it will be obviously abelian. So that's an inference. And then, so together this V, how many things we have? V, then you have this vector addition, and then you have this scalar multiplication with the scalars from in F. So these are the three things which we just get an inference from. Um, this is obviously true. And let's see how we get some more idea about these vector spaces. So normally, if all the above properties are satisfied, we say that V is a vector space over the field F. So the over the field F is really important as we say and notate we along with our vector space we always have to mention about the mention about the field F. Okay, the name vector is applied to the elements of the set V. And let's see, check out the first example. It is the n tuple space and we call it F raised to n. Okay, let F be any field. Let V be the set of n tuples alpha is equal to x1, x2, etc. xn. So we have V to be set of all x1, x2, etc. xn. Okay, where each xi's are coming from F. Okay, F is already given. Now, and you call it alpha for convenience. And if beta is equal to the n tuple y1, y2, etc., yn with yi is coming from F again, that means obviously that is coming from V. We are defining the sum alpha plus beta is equal to x1 plus y1, comma x2 plus y2, comma etc. xn plus yn. So what is this operation? The plus here. So we are defining it like this. So when we are defining, we give a column here. So this plus is nothing but the addition inside the field F. The field F already has an addition. That addition is this. So we are defining the sum of two elements inside this V as the component wise addition, and that addition is happening inside the field F. So that is well defined. And then we are going to define C alpha as Cx1, Cx2, etc. Cxn. So here there is an addition, right? So this addition is happening inside, not addition, this multiplication. This multiplication is happening in between multiplication inside F, right? C is coming from F. Scalar C is coming from F. C is from F. And obviously x1, x2, etc. xn are from F already. So it's just a multiplication inside F in the field F. Okay, so that is also well defined. Now what do we have to check? That this vector addition and scalar multiplication satisfy conditions that we mentioned earlier. That is a basic verification of whether the addition is commutative, associative, whether there is a zero vector, where there is an inverse for every vector, and these four properties. So totally there are 8 properties which you have to verify, which are very simple, and you can try them out and see that you get that this is actually a vector space we are talking about. So what is the vector space? Here the vector space will be V, where we are taking the n tuples, right? Fn, V is equal to Fn over the field F. So we have specified what the field is. So this is the first example we are talking about. Now let's see the second example, which is the set of m by n matrices, and they are denoted as F raised to m cross n. Let F be any field and m and n be any positive integers, and we are taking F, denoting F raised to m cross n to be the set of all m cross n matrices over the field F. The sum of any two vectors A and B. So this is the, so basically V is equal to, here you are having this. This is the set of all m by n matrices where the entries are coming from F, right? Okay. So the sum of two vectors A and B is denoted by A plus Bij is equal to Aij plus Bij, which means the ijth entry is added to the entry of the matrix. Similarly, the product of scalar is just C multiplied with each entry of the matrix. And this can be verified over the field F to be a metric, to be a vector space, the matrix. Now, the example 3 is an important example. Let F be any field and let S be any non-empty set. V be the set of all functions from the set S into F. The sum of two vectors F and G in V is the vector F plus G, that is the function F plus G of S is equal to F of S plus G of S. The product is CF into CF of S is equal to C into F of S, and we have to check out whether this definition, the definitions of addition inside this vector space and the scalar multiplication inside this vector space satisfies all the 8 properties which are required for verifying it to be a vector space. We cannot call the space as a vector space unless we check out all the 8 requirements. Okay, so what are the 8 requirements? So first one is we define the addition. We have to see if it is commutative. Definitely it is commutative because we have taken the, obviously the field is F and S V and E. Now this set, and V is the set of all functions. So what is V? V is the set of all functions from S to F. So this is V, right? Okay. Now this functions are always, especially the normal addition, they are commutative, right? And the addition is associative. So what is this? This is nothing but F plus G of S. This is equal to G plus S of G plus F of S, right? So here this will be F plus G plus H of S, and this is nothing but F plus G plus H of S. So associativity is also satisfied. The zero vector is a zero function, and minus f of s will have minus f of s, which is a function defined as this, and you get from that you get f plus minus f of s is equal to 0, 0 of s, just a zero function, that is 0. So you get the four criteria for the addition, and similarly you can calculate the four criteria for scalar multiplication, which you should work out and verify about the it being a vector space. So it is a vector space. That is a third example. So you know, third example is a set of all functions, as we said, from a non-empty set S to the field F. So this is field F, right? Over the field F. So this is the third example. And please do verify the 8 criterias. The next one is the space of all polynomial functions over a field F. So let F be a field and V be the set of all functions from F to F, which have the rule of the form. So you have a field F fixed, and V is a set of all functions from F to F. That means the coefficients are coming from F, okay, which have the rule of the form. It's of the normal polynomial form like this. Okay. Yes, we said the scalars are coming from F. It's called the polynomial function on F. Normally, it is a polynomial function. Let addition and scalar multiplication be defined in example 3 as earlier, like this. Two functions can be added like this, and scalar multiplication like this. Okay, then you get that if f and g are polynomial functions and c is in f, then f plus g and cf are again polynomial functions. Obviously, they will be of a form like this, and we get the 4 plus 4, 8 criteria, which you have to verify and see that set of all polynomial functions. Set of all functions, the form of c naught plus c1x plus etc plus cn x raised to n, where ci's are coming from f, okay, over the field f. Obviously, the what should be specified, the addition and scalar multiplication also should be specified. How are they defined? Scalar multiplication. So in each example you have to specify that also. What is the addition here? Addition of vectors. What is the scalar multiplication here? Similarly, for here also, they are defined. The addition, the scalar multiplication. Here also, this is the addition, the scalar multiplication. So all the points should be mentioned rigorously like that. And let's see the example 5, which is the field C of complex numbers, which can be verified over the space R. That means if B is equal to C over the field R, and with the normal addition and multiplication. Let F be the field of real numbers and B be the set of n tuples. Define addition of vectors and scalar multiplication. In this way, we obtain a vector space over the field R, which is quite different from the space C raised to n and space R raised to n, right? Uh, so this is an important example, C over R. So don't forget to, when you verify the, to mention what is the addition and scalar multiplication involved in this vector space in order to verify. So if C is a scalar and 0 is a vector, then we have C0, C into 0 is equal to C into 0 plus 0, because that is the additive identity, which is equal to C into 0 plus C into 0 by the associative role. And C0 is equal to C0 plus C0, that means C0 is nothing but 0, right? Similarly, for any scalar 0 and any vector alpha, we can get that 0 into alpha is equal to 0. If C is a non-zero scalar and alpha is a vector such that C alpha is equal to 0, then C inverse of C alpha is equal to 0. But C inverse of C alpha is equal to C inverse of C into alpha, which is equal to 1 into alpha, which is equal to alpha. That means alpha has to be 0. Thus, we see that C is a scalar and alpha is a vector with C alpha is equal to 0. That means either C is the 0 scalar or the 0, the alpha is a 0 vector. If alpha is any vector in V, then 0 is equal to 0 into alpha, that is equal to 1 minus 1 into alpha, that is equal to 1 alpha plus minus 1 into alpha, that is equal to alpha plus minus 1 into alpha, from which it follows that minus 1 into alpha is equal to minus alpha. Also, the associative and commutative properties of vector addition imply that a sum involving a number of vectors is independent of the way in which these vectors are combined and associated. So you get properties like this. Now the important definition is the linear combination of vectors. A vector B in V is said to be a linear combination of the vectors alpha 1, etc., alpha n in V, provided that there exists scalar C1, etc., Cn in F such that beta is equal to C1 alpha 1 plus etc. plus Cn alpha n, which is equal to summation I is equal to 1 to n Ci alpha I. So this is the definition of linear combination. And also you can see if we are given points P and Q, how you can geometrically uh, see how we define the vector addition. So if P is equal to x1, x2, x3 and Q is equal to y1, y2, y3, like this. The When we add both of them, what you're getting is actually the diagonal of the parallelogram formed by this vectors OP and OQ, which we know what is vector addition. is. So the newly formed vector is nothing but the diagonal of the parallelogram. And similarly, scalar multiplication can also be given a geometrical interpretation. That is, if C is a real number, then the product of C and the vector OP is in the vector form, then that will be the from the origin, and that will be the modulus of C times the length of OP, and in the direction of the same as that of OP, that is scalar multiplication given a geometrical touch. And, similarly, such linear combinations also can be understood by a geometrical way, which you can read out through the page 32 to get an idea in a nice way. And let's start out by doing exercises from 1 to 7 of this section. So, thank you for watching out the lecture. See you in the next section. Till then, bye.